I will have you all muted when you first come in. We're all set to mute now. If I ask if there are any questions and I receive zero response, I assume that there are no questions and we can just keep going. I did take a look. I will also record this so you can rewatch whatever is needed. Your next test will be on October 25th. You should see that reflected in your assignments now. I just added it. So we should see that down here, due October 25th. It says at 6 p.m. That's when it starts. Well, that's when the class starts. So that class will start with a topic of centroids and center of gravity. I am going to probably honestly cover this a little bit here because I know attention span before the test is a little limited. So what we're going to do is quiz 2 covers, here we go. Test 2, quiz 2 focuses on the materials on week 3 and 4. It covers materials from 1 to 4. Really, the week 1 and 2, we're carrying over some concepts, but we're not going to focus here. So things like, I don't know, force balancing, equilibrium, those things will kind of carry over. But our focus is on week 3 and 4, meaning also on these 2 homework assignments. And of course, I'll give you a little bit of more guidance on where you'll study. But you know that that's coming. So if this is an old syllabus. So we're working off of your syllabus here. That'll be October 25th. We'll do that test. That means the next 2 weeks, it's particularly important to come to class. You know, a little ironic of me to say that. As I say that, let me also say thank you for your patience in this kind of shuffle of things. And I'll post this so you can rewatch it if you need to. But try to be at class next week because we'll do some review for the test and then definitely be there for the test. You don't want to miss the test. If you miss the test, then it's the grade that gets dropped. There will be nothing about couples on your test. There will be moments on your test. There will be moments, but not couples on your test. Equivalent force couple systems will not be on your test, and equilibrium of a rigid body will not be on your test. That is technically next week's topic, but we're going to start introducing it today a little bit. That all being said, so today's new stuff will not be on the test, but it does still apply. So that being said, I took a look at the check-in and the things were, 1, to post the homework. I'm not going to post all the homework solutions I'm not going to post the homework solutions, but there are some solutions of the past homeworks in the slides. The other question I had was to post the slides. I know I've not been the best with that, but they are posted now. You should see week. You should see through week 7, which is next week. And so you should see all that there, and they do include questions, homework questions on them. So you do have some solutions there. If you reach out to me, send me a Canvas message, I'll send you and ask for a specific solution, I can send it to you. Okay, so couple systems. We introduced them a little bit. Let me know that I say that. Let's reopen. So if you remember, couple example. So a couple is going to have, a couple is going to have a positive and a negative force. I guess I could just go with this one. A positive and a negative force. I don't know. Let's go with this one. So this was your second homework question. This was your second homework question right here. So our 60 pounds, that is one couple. So we have parallel forces in equal in magnitude, opposite in direction. Same thing with our 40 here is our 40 is a couple. When we were talking about moments, a moment is your force times the perpendicular distance, right? The moment of a singular force is the force times its perpendicular distance. The other way we calculate that is with cross product. The moment of a couple is the magnitude of one of those force magnitudes times the perpendicular distance between them. If you were to evaluate this point, that would be the moment from this force. If you were to evaluate this point, that would be the moment from this force. If you were to evaluate anything in between, they would add together. If you evaluate anything outside, this would be a larger moment, but this would subtract from it, and we'd end up with the same moment. So having couples allows us to, replacing our moments with couples allows us to move that force around our diagram without impacting our equilibrium conditions in the same way. So let's go in with the homework question. Let's start there. So the first one is a tricky one. The reason this is tricky is because our brain naturally wants to say, so we have two forces of 66 newtons applied at the corners. Your numbers may be slightly different, but the concept will be the same. A and C, 200 millimeters square plate. So we know these two distances. We want to find the moment of the couple formed by the two forces by multiplying their magnitudes by the perpendicular distance between them. By definition, the moment of a couple is the forces multiplied by the perpendicular distance between them. The trick here is it looks like your perpendicular distance, your brain wants to say that A to C is that perpendicular distance, but it's not. Remember, the perpendicular distance, we want to extend these on through their line of action ongoing. And the line would hit it in a way that it's like a right angle. It's perpendicular. That being said, so if this is 90 degrees, because we know that's 90 degrees. If this is 90 degrees, a right angle, half of that would be 45. 60 plus 45 is greater than the 90 that we need to hit that perpendicular distance. So we kind of have to overshoot it. We're going to go past it. And what we're going to do is we know that this is 200 millimeters. And so we can use that geometry with the 30 degrees here, right? 30 degrees to get 30 plus 60 is 90. 30 degrees is also sharper than our 45. So it's going to hit DC rather than hitting CB, right? If we went on a 45, we would hit C. If we go on an angle closer to this axis, we're going to hit DC. And if we go on one closer to the AB axis, we would hit CB. Since 30, we're going to go up and hit DC. Are there any questions up to this point? Cool. So once we have that 30 degrees, we have that AD is 200 millimeters. Since we're going to our moments, since we're using moments and moments are Newton meters, we do want to go into our meters as our unit. So make sure you do make that adjustment. So 0.2 meters rather than 200 millimeters. But we can use our geometries here to find where on this line we would intersect. Actually, let's go down one more. So this is the textbook version. And so they just do it in less steps. This is my version. I took that length and the cosine of 30 to find this diagonal length here. So the lengths that I want to find here, I want to find this diagonal length because that plus E prime to E prime is a point I made up right here. Those two added together are going to be the perpendicular distance. So I need that value. The other value I need is DE prime, because knowing that, if I know DC is 200 millimeters, DE prime, so we could get E prime C from subtracting DE prime from that 200 millimeters. To get that E prime to C is 0.0845. Why that's important is because we want to figure out this E prime to E, that little additional bit of distance there. Have I lost anybody yet? Cool. Our last portion, so we know our E prime to C, we found that on the last slide. So the cosine of 60 is going to equal E prime over E prime C, that length that we just calculated. So this gets us this last length here. So then our perpendicular distance will be AE prime plus E prime E. Maybe I should have picked a better name, but that's what we're stuck with. So we end up with that perpendicular distance being 0.27. We would expect it to be more than either of these side lengths, right? 0.27. And so our moment equals our force magnitude times the distance between them. Each has a force of 66 newtons. 66 times that distance we calculated gets us 18 Newton meters. If we were fixed at any point in between them, right? My brain wanted to go if we were fixed at, because I'm so used to our moments based on points. But disregarding that, if these two forces were applied here, this object would rotate in a clockwise way. So either designate that that is clockwise or have a negative 18 Newton meter value there. Questions here? Okay, cool. That is a tough one. The trig makes it more difficult, and also that kind of like sneaky move there that makes you think that you're doing something wrong. Second question. So this one and this one are two that I think are good practice questions that I do enjoy, that I think fit the kind of syllabus well. So this was one that I used to give the example of a reminder of what couples are. So here we have 4 pegs, the same diameter, are attached to a board, strings are pulled. We want to find the diameter of the pegs, knowing that all of these two couples add up to a couple or a moment of 1,142.5 pound-inches. And that will be occurring counterclockwise, which we should be able to see on this image here. So here, our forces, we have our forces. Our force magnitudes are 60 and 40. We have the perpendicular distances between them. So they give us center of the peg to the center of the other peg. But our strings, our forces are attached to these strings that go around it. So we're going to add a radius here. So let's look at the 60 first at a diameter of 12. So DBC. We have a radius here and we have a radius here. So it's going to be 12 plus 1 diameter value or 2 radius values. Our 40s, same type of thing. I'm sorry, our 40s were our 12 away. Our 60s were our 9 away plus D. Doing that, so we have our moment magnitude of 1,142.5 is equal to, we have this in parentheses multiplied by FAD, if AD is 60, plus, put these in parentheses, multiply by FBC, that's by 40 pounds. So you're going to have then 2 terms with D in it, 2 terms with a value over here, and we can use our algebra to solve for 1.225 inches. Questions here? This one's a little more straightforward. We have this plywood. Well, no, I don't know if that's true. It's about similar, more straightforward than the first one. We have plywood with we know that it's having a 16 Newton meter couple applied to the plywood. Determine the magnitude on nails based on knowing this, based on the location of the nails. So our first set is at A and B. A and B is 450 millimeters apart, or 0.45 meters apart. If we know that our moment is 16 Newton meters, Our force times our perpendicular distance, or the distance between them, perpendicular distance between them, would be, so our 16 divided by our 0.45 should give us 35.6 newtons as the force magnitude there. Questions here? Cool. If you do have a question and I keep going, you can interrupt me. B and C, same thing. So once we have the equation, it's kind of just, well, we know the equation, M equals FD, it's identifying the forces or it's identifying the distance and then working backwards because we do have our moment already. So here the distance is 0.24 meters, 240 millimeters. So our 16 divided by 0.24 is going to give us 66.7 newtons. And our final one would be that diagonal. So the only trick here is that you're going to have to find the distance from A to C. It's going to be the square root of the sum of the squares. So it's our right triangle here, right? 450, 240. A squared plus B squared equals C squared. C squared would be our A to C. So our perpendicular distance equals the square root of 0.45 squared plus 0.24 squared. That's going to give us 0.51 meters. So dividing 16 Newton meters by 0.51 meters should give us 31.4 newtons. Questions there? Okay. This one is a tricky one, and I want to go into kind of take a look at a simpler version of this, or maybe more one-dimensional, two-dimensional version of doing that. Actually, let's start with here. I know we've looked at the slide once before, but once or twice. All of these couples are equivalent. They are equivalent because they are in parallel planes. They cause rotation in the same direction, meaning clockwise, counterclockwise, on a parallel plane. And they have the same magnitude. Lost my thought there a minute. Have the same magnitude. So our first one is going to be 20 times 6. Then we have 30 times 4. And this one's also 30 times 4. We're just lifting that plane up. No matter what, they all are causing the same rotation around the same vector. Remember, the vector we get for moments is actually the vector that we're wrapping around. So we're wrapping around this. In this case, it would be the I vector, right? Because we're wrapping around something parallel to the Y vector. So we're wrapping around that and are getting a rotation. If we're looking down at the XZ plane, we would be seeing it in a counterclockwise way. All of these have the same impact. When we separate moments we can add together. This is where we're kind of going. So MO prime, picture that. So this is our equation for when we're moving a force and we need to account for the change in the moment due to that moved force. So moment O prime, think of that as your new moment value, or your moment at your new location. So I'm going to go back to that first problem, but we're going to find a better one to do a practice round. But in this case, your new location would be where are we trying to move that force couple system to, and we're trying to move it to H. So MO prime, in this case, it would be MH. MO, so your MO prime, or your new moment, equals MO, or your old moment, or your moment at your old location, or your moment at your previous analysis. So in that first question, it would be your moment about A. So this is your adjusting for your moment at H, basing that off of the information you have about your moment at A, or your old moment value, plus S is going to be the displacement vector. So what did you have to do to go from your old value to your new value, or rather from your new value to from your old value to your new value, your old location to your new location. So that would be that vector that brings us from A to H, crossed with the force vector, and that will adjust for that movement. I find this to be harder conceptually when I just speak it out like that. And I think that is a good problem. This problem is really good for simplifying it. We have so next week, and possibly we're going to touch on it at the very end of this if we have a little bit of time, which we will. But we're going to start doing adding reaction forces. So next week we'll start adding a force. Here would be a pin joint, meaning it is applying a force, holding it in place, both vertically, horizontally, and the only rotation you have is a rotational freedom there. This is a roller, so you're allowed to slide back and forth left and right or along the x-axis, but you would be applying a force or a resistance here. It's not happening yet, but it is coming, so just a little teaser, I guess. But this question, for the beam, reduce the system of forces shown to an equivalent force couple system at A, an equivalent force couple system at B, and a single force or resultant. So starting with the equivalent force couple system at A, in order for, let's forget about the couple element, in order for it to be an equivalent force, we would need the sum of the forces in X to be equal and the sum of the forces in Y to be equal. So in this, we don't see any forces in our X direction, we only see forces in our Y direction. Our summation of forces in Y direction should be the only vertical force that's applied, which means that our force at A should be positive 150 minus 600 plus 100 minus 250. That would come out to negative 600 newtons. So our resultant force is still just adding those components together, right? We only had Y components, so it was already separated for us, or J components, so it's already separated for us. Our resultant force is still just the sum of those. Our moment here. So now if we applied all of our forces to point A and then evaluated the moment at A, if we didn't have this moment here, I'm covering it with my finger like you guys can see that. If we didn't have this moment on the side and we only had this negative 600 and we evaluated the moment about A, it would look like the moment about A is equal to 0 because that force goes through that point and our perpendicular distance is 0. But when we look up at this one, we can tell that's not the case. We have a moment from this 600 applied at 1.6 away. We have a moment from this 100 applied at this away, and a moment from this applied at this way. So we need to account for that. So our summation of moments at A is equal to the summation of moments. When we're applying the couple, we'll apply a couple that's equal to the moments that these forces would apply. So add our moments together at the first, whether you count it or not, 150 times 0, because our perpendicular distance is 0. That's our first term, if you want to count it. 600, I believe these are all newtons, 600 newtons times 1.6, right? Force magnitude times perpendicular distance. If we were fixed at A, this would cause a rotation in the clockwise direction. So this is going to be a negative value. So 1.6 times negative 600. Our second value is going to be this perpendicular distance of 2.8 times 100. That's going to be in the opposing direction, or counterclockwise direction, and our positive direction. So that'll be positive. And our last one will be a negative 250. We already figured out that based on this point, our negatives over here will cause a negative moment. So negative 250 times 4.8, and we have that as our last term. Solve this, do your arithmetic here, and you're going to get a moment of negative 1880. Remember, negative means we're rotating in a clockwise direction. Are there questions here? So in this case, our equation of, I'm really bad at writing on the screens, just so you know, but our equation of MO prime, our O prime would be the moment that we're moving to, right? So we're moving to A equals the original moment, or the moment that was originally applied, or where it was. I'm not even going to account for that, right? I'm going to say we have our cross product equals our perpendicular distance. And so we're already accounting for that. if we had something like on our original problem that there was already a moment, a positive moment of 880, then we would have our MA equals positive 880 for our original moment. This would be our MO then, plus this value, the R cross element. Questions there? I think the next part is also helpful in the same context. Oops. Okay. Part B, we see that equation a little bit better. So part B, we already summarized our system. In part A, we summarized our system into a system at A. So now we want to find the equivalent force coupled system at B based on that. Summation of forces in our x direction is equal to 0. Summation of forces in our y direction is negative 600. That is not going to change. Our negative y forces are going to stay the same. So we apply that negative 600 over here. Our equation M new location, MO prime, M new location, M sub B, the moment about B, is equal to the moment about A, right? We have that external moment, that negative 1880 that we applied, plus the distance that you're moving, your R, your displacement, crossed with your force. In this case, we're calling our force our resultant, so we're saying R, and that will get you your final equation. So we have our negative 1880 from our original look, our original analysis. We're moving this 600 by 0.48. And in moving that, it's going to, let's see, how do we phrase that? So if this force, so looking at the original, analyzing point B, the moment is pushing clockwise, and that force would push counterclockwise, and so they are opposing. So we have our positive and then our negative, or negative and then our positive. Questions here? Okay. Let's go to, let's take a look at this one before the homework one. The one thing with this question, so this question is very similarly structured to your final homework question on your last, that box where you move from A to H. However, when I look at this, you guys know I don't like my, I like to do, our class is mostly focused on unit vectors using like locations. So like our question that we have for homework, it has like labels on the dimensions. This one, and where it differs is that it has some angles. So you have to find the unit vector using cosines, which is not my favorite. And then also the solution does have a mistake. So our B to E, that one you can find the unit vector using the geometries. That's what I'm more concerned with you being comfortable with. But finding the unit vector for this 1000 newtons and this 2000 newtons is a little bit less of what we focus on in the class. So my focus again is this. The unit vector here, so we're looking at B to E. The unit vector for that force is equal to the line that connects them, divided by the magnitude of that line. A unit vector gives us direction with no magnitude. So we could also look at this as the vector is equal to the unit vector times the unit vector, I'm sorry, the vector magnitude. So that's how we're going to calculate our B to A, I'm sorry, our B to E force. For our FC and FD, those unit vectors are going to be calculated using the cosines. And for FC, this should be cosine I and cosine Z. This minus cosine 45 J should be K here. And it does change in the next slide, but it's just a mistake here. So 45 degrees is from parallel to the X and 45 is from parallel to the Z. And then this one, our 1200, we have 30 from parallel to the Y and 60 from parallel to the X, 60I, 30J. This is where I would prefer, know this. This is more mathematically based though. This is the focus. Either way though, know that your force vector is going to be, or your tension vector is going to be the magnitude of that force times the unit vector. So similar to how these geometries show us things, if the unit vector is, right? This is the rewrite. So the force vector equals the magnitude, that gives us the amount information, and our unit vector gives us the direction information. Questions here? Cool. Our equivalent forces here. So the purpose of finding the unit vectors is so that we can break apart our forces into their X, Y, and Z components. That's the easiest way to do that. So now we have all of these forces in their X, Y, and Z components, our equivalent force coupled system. We know our forces in the X need to be equal to what they were, our forces in the Y need to be equal to what they were, and our forces in the Z direction need to be equal to what they were. What they were is the resultant of those three, and so we can sum them. So our resultant force, our X element, will be the sum of the X elements, our Y element will be the sum of the Y elements, and our Z element will be the sum of the Z elements. That element is saved from on your homework question. For each of these, so this one now doesn't have a moment, so we don't have to worry about moving that moment. But remember, when you have a couple moment, it's easier to move. However, we moved all these forces, so we have to account for the moment impact of those movements and add a couple that accounts for those changes. So we'll start with B to A, so that's our first force, or 700 Newton force. So we're moving from point B up here to A. What is that? What does that look like? Okay. So we're going positive X direction, same Y plane, right? And our K value is going to also be positive. I think I misspoke there. So we're going from A to B. From your new point to your old point would be your R vector. I struggle when I subtract them. When I subtract them, sometimes I end up with the wrong polarity, meaning I could get negative, 0, and negative. Then I look here, look at the directions we're going, and see if it makes sense. So think of it as that there was a force here. What was that force's impact on this moment? And that's why that sense is in that direction. So our force magnitude for our first one was 300 minus 600 plus 200. We're going to do the cross product of these. Remember, we're going to go positive in this direction, sum them together. So we would have a J and a K value. And then in the negative direction, we would go, this would be our negative direction. So I times 0.05 times 600, J times 0.075 times 200. These are all negative values then. So negative, negative, negative K times 0 times 300, and sum those together. Repeat that for each of the force movements. And our moment resultant is going to be the sum of the moments. So we sum all of those together. This one is intricate in having the multiple forces and having the cosines. Usually you're not going to have to do this many movements. Questions on any of that? Okay. So then I'm going to go back up to that homework question. Here we are. Okay. So let's try this one again. So we have a 70-pound force. Our force is going from A to J, so we have the unit, we can get the unit vector, we can get the direction, we can separate that into its elements, X, Y, and Z elements. And we have a moment, we also have the moment vector. And so we can, and the moment magnitude, so we can figure out that as well. So I guess the geometries that make up the vector. Replace the given force couple system with an equivalent force couple system at H. So we are moving from A to H. So our R vector will be from H to A. Our distance from H to A, we have, I'm sorry. Let's start with our unit vector from A to J. So the unit vectors will need our A to J, A to C, and A to H, or H to A. So our A to J are locations there. We have, along the x-axis, we move 18 inches to go from A to J. Along the y-axis, we move downward. It looks like this is parallel with the bottom face here. So let's say we go downward 14 inches. And in terms of the z direction, our z direction is going to go forward or backwards. It looks like it went backwards a little bit, 3 inches, so -3 inches in the z direction. So our A to J vector, 18I minus 14J minus 3K. The magnitude of that vector will be the square root of the sum of the squares to get us 23 inches. Our force, so this is kind of overlapping some steps, right? This is saying, so we've said unit vectors equal your distance vector divided by your distance magnitude, right? And then also that would also equal your force vector over your force magnitude. So they cut out this element of having the unit vector individually. This would be the unit vector. 18 divided by 23 in the I direction, minus 14 divided by 23 in the J direction, minus 3 divided by 23 in the K direction. That would be your unit vector there for A to J. They just kind of clumped it all into one and said your F vector. So looking at these two equations, your F vector equals your F magnitude divided by your magnitude of that displacement times the displacement vector. That's what they did there. So they just kind of grouped some equations. Questions there? Okay. To get your final force vector, same thing with our moment. So our moment, we're going from A to C. We're going to move 45, -45 in the x direction on the same plane. So we're on the same y level. So no change there. And then we are going from, so if this is 3 and this is 25, then A to B or A to C, we're moving 28 in the negative z direction. So this would be our unit vector for M, -45, I'm sorry, would be our direction of M. Find the magnitude of it, square root of some of the squares. This would be our unit vector for M. So 1 divided by 53 times -45I minus 28K. So we distribute this, it'd be the same as -45 divided by 53 in the I direction minus 28 divided by 53 in the K direction. Multiply that by our moment. So in the same way that our unit vector, I'm not going to do all the vector symbols, but equals D, I'll do it over here, over the magnitude of D. I'll say absolute value just for my own sake. Your force over your magnitude of force. Told you, I warned you about it. Your moment divided by the magnitude of the moment. You can find the same type of thing. You can use this distance vector to find your moment vector. I would say cut this out. That's not going to equal because your force isn't going to equal your moment. But using your unit vector to find the same information is still valid. So We then multiply our force magnitude or our moment magnitude given in the problem statement by that unit vector. I don't know why this m is out front. I think it's a mistake. So then m prime, or the moment at the new location, mo prime, equals m, or your moment at the old location, mo, plus rah, the vector from h to a, crossed with f. So our old moment, we have that moment vector. We just solved for it. We didn't all the way solve for it, but this is what it ends up being, the original moment vector. Add to that r cross f. So I is our first column, is going to be our unit vector values, lambda values. These would be our r values, and these would be our f values. Once you get the cross product of this, you add that here, and we get a final answer of, so the force we already solved, 54.8 pounds in the I direction, minus 42.6 in the J, minus 9.1 in the K direction. Our moment would be negative 2030 in the I direction, pound inches in the I direction, plus 410 in the J direction, minus 3867 in the K direction. Just a little bit of rounding. Questions there? Okay. I think we lost 2 and gained another, but I'm not positive. It will be recorded, so if anybody came late, it is recorded. And I do definitely recommend you look at the beginning, because I'll talk about the test a little bit. But we're also going to go into it a little bit more. So this one, I don't think we'll have much to look at. This one, I think we're good. Where are you at? Let's go to, I'm going to go to next week's. We'll end with some test review. And the reason I'm doing this is that so next week, we can focus a little bit more on test review. Your test will be on the 25th. So this is technically next week on the syllabus, which means that this homework you have not done yet, but that doesn't matter because it's not bad to look at it yet. We'll look at it more next week too. So we know that all of these beams are 4 meters long and they're subject to different loading patterns. Replace each loading with an equivalent force couple system at end A of the beam. So let's start with A. So here is what we have. Our summation of forces in X is equal to 0. Not an issue. Summation of forces in Y is equal to negative 400 newtons minus 200 newtons. So our resultant is negative 600 newtons. Questions there? Okay. Then our moment is your new moment. Your moment at A is your original moment plus the change from the movement of your force, right? So our original moment is 1800 Newton meters in the counterclockwise direction, or the positive direction. If we're fixed at A, the force at B would be causing a clockwise rotation, so that would be negative, countering what we, the 1800. And so we're going to subtract 200 newtons times the distance we're going to move it, 4 meters, to get 1000 Newton meters in the counterclockwise direction. Questions there? This one, we're not going to see a change, right? This is a moment due to a couple, and so it gives us that mobility element to it. 4 meters long beam, subject to a variety of loadings. Summation of forces in Y is still 600. So our force is still 600. And our moment is 900 in the clockwise direction, so negative 900. MA equals M old plus the linear forces that you're moving times their distance that they were moved. So no linear forces, no distance movement. Well, linear forces of 600, but no distance moved, 0. So our moment is still the same of 900 or negative 900 Newton meters. 900 clockwise or negative 900. take a look at some more of these. Let me take a look at this and see what could be a good one. Let's look at the first one with 2 moments. So let's look at E. Okay. E, summation of forces. We have a negative 400 and a negative 200. Add those together. We should have a negative 600, so a little typo there as well. Our moment about A. So we have this 200 Newton meters and this 400 Newton meters that will add together, both going counterclockwise. They're going to add to each other. So 600 Newton meters. And then the force that we need to move. So we need to move this 200 Newtons, the length of this beam, which is 4 meters. So if we were fixed at A, this 200 would counter these rotations. So we're going to subtract it from them to get a final 200 Newton meters in the clockwise direction, or negative 200 Newton meters. Questions there? Okay. Your next homework question we'll do, and then the last one we'll look at, and then the last one we will briefly look at. That one will be more of a focus next week. I'll give you hints as to how to approach it more so. So we have 2 children, A and B, sitting on a seesaw. Child A is 68 pounds and child B is 48 pounds. We want to find the position of a third child so that the resultant will pass through C, meaning that the moment evaluated at C is equal to 0. That's another way to say that. And the third child is supposed to weigh 52 pounds. So I'm going to start by creating my free body diagram. So I have this point C labeled here. I have child A at A, weight of A, so this should be 68 pounds. This should be 48 pounds. And then the new child, logically, I can figure out that if they're both 6 feet away and child A is heavier than child B, our third child needs to be closer to child B. If we assumed wrong, we would get a negative value. And that would tell us that we assumed wrong. Assumed or reasoned, logicked wrong. So evaluating the moment about C, there's 2 ways we could go about doing this. So the moment about C is equal to 0. I have the equations. Okay. The moment about C is equal to 0. Are 2 options for doing that. The one is your moment is equal to 0, and so then if we're fixed at C, rotation at A is going to cause a counterclockwise direction, which is, or rotation, which is positive. That's 68 times that 6 feet. If we were to apply this weight, that's gonna, to counter that, if we're fixed at C, that'll cause a clockwise rotation. So we're gonna say negative D is our perpendicular distance that we're trying to figure out, times the weight of the third child is 52 pounds. Bonus child. And then minus weight of child B, distance child B, the weight is 48, and the distance is again 6. So again, all of this will equal 0 because we have equilibrium at point C. Questions there? Okay, cool. The other way would really just be, it's the same exact thing, it's just different thought patterns. But to say, okay, so since all of my forces are going to say, okay, anything that causes a counterclockwise rotation is going to go on this side of the equation, and anything that causes a clockwise rotation is going to go on this side of the equation. So then on this side, we're going to have the weight of child A is 68 times 6, right? This is still the moment from the 68 force at 6. That's going to equal the moments from this side, our clockwise moments of, I'm going to start with the first child B, 48 times 6, plus 52 times D. And then we solve for D. Questions there? These 2 equations are the same thing. It's just a matter of your thinking patterns, if you like to set everything to 0 or you like to balance equations. Okay, cool. I'll let you do the second part yourself. It's a very similar approach. You're just changing the weight of the child, and that's going to change the distance that they need to be at. This last one, we can simplify this significantly. So here we have the roof of a building frame is subject to the wind loading shown. A1 equals 230 and A2 equals 230. So I don't know why they gave us, probably so they can have multiple questions with the same diagram, but A1 and A2 are equal. So now when I look at this, I'm seeing, I want to make this easier on myself, right? The way it's set up right now, there's a lot of forces going in a lot of directions. And it's overwhelming. We can find the unit vector directions of these by knowing they're perpendicular to this roofing. And we know the dimensions of the roofing. We know that there's a 10 vertical rise with a 30 horizontal lateral movement. So we could find the slope of that, and then these would be perpendicular from that. That is not a common thing that we'll do in this class either. This is kind of the one time you'll see that. Maybe 2 or 3 times maybe you'll see it in the class. But either way, when we separate this into the 2 halves, now I see when I look at this, so let's go back to, when I look at this, there's a line of symmetry down the middle here. This line of symmetry has equal forces at equal distances on either side of them, right? So if we were to evaluate the moment about this point, this 400 is going to cause some rotation at whatever distance, and this 400 will cause an opposing rotation. This A1 will cause a rotation, this A1 will cause an opposing rotation. And so that middle point, that line of symmetry, is going to be have no moment impact in this when we're only looking at this first half. So I keep forgetting to do this. So if I wanted to, I could, right, if the moment is equal to 0, we can put all of our forces there. So this force would be your 400 plus 400 plus 230 plus 230, accounting for the magnitude of all of them, but balanced in how they would impact your moments, right? Likewise, on the other side, there's not symmetry in the whole unit, but there's symmetry on each side of the roof, which allows us to reduce this from an 8-force system to a 2-force system, right? So now this one's going to be opposing, but same type of principle. So the only thing is this has the positive X value, positive Y value. This has the negative Y value. The same thing, 400 plus 400 plus 230 plus 230. Questions there so far? My version, I'm looking now, my version is a little different from their version. So actually, no, it's not. They just don't necessarily state that that's how they got to this 1260. By replacing the loading on each side of the roof by a single 1260 force, we get 1260 times, and then you're going to have the unit vector. The unit vector is going to be inverse what this unit vector is. So what are we looking at? Which side are we looking at right now? I believe this will be this side. No, that would be this side. Where did I just... So this would be your left side forces, and this would be your right side forces. Your I, positive I, is the positive rise in the 10. 30J is the 30 lateral. The reason they switch positions is because of that perpendicular element, right? That instead of giving us the direction of these forces, they gave us the direction of this. So if it helps you to just know that this is the unit vector with just an adjustment on, you're going to have to pay attention to your y value. Is it positive or negative? So the unit vectors of these are not equal, but the only difference is the y value. Does that make sense? Okay. The last thing here is determine the line of action of the resultant of the loading. That is also not something that's super significant, but what they're saying is if you followed those lines, that intersection where their resultant force would have no moment impact. So essentially it would be in line with both of the forces. Does that make sense? So you're analyzing then where the moment impact would be 0 in perspective of the whole image instead of just each half. Does that make sense? Okay. We will look at this one. So I want you guys to tackle this one at home, and then we'll come back and we'll look at it next week. And then we're going to go this is sound now. We're in next week's content, going into next week's material. I'm going to do a little bit of a briefer, faster version. Next week, we will do both this review and, both this material and test review. Okay, so when we're looking at our rigid bodies in static equilibrium, what that means, summation of forces equals to 0. There's no lateral movement. There's no translational movement. That's what we saw with our particles. The other thing we have with our static equilibrium is no rotational movement. So when we're rigid body versus point, rigid body has shape, structure, etc. So we now have to consider moments is essentially what I'm saying. Our moments need to be equal to 0. The summation of our moments need to equal 0 in order for our free body, rigid body, to be in static equilibrium conditions. So one thing that's going to happen is our free body diagrams are going to change a little bit even more so. So again, our free body diagrams, we want to figure out the boundaries of our diagram. Set up those boundaries. Anywhere where you broke through a material, you want to add a force. So here we have our negative force due to the weight. Gravity, the weight of a machine is a little bit harder to usually see/know, but the problems here will usually help you out with that. So our force due to gravity. Over here we have a pin joint and a rocker. A pin joint, pin joint, this is welded to this surface or somehow fixed to the surface, welded, bolted, etc. And then there is a pin that has rotational movement in there, the ability to rotate, but you cannot, like if I were to pull this outward in the X direction or the Y direction, it will not allow me. In any way that it is constraining movement, I'm going to introduce a force. So this will not allow me to push into the wall or pull away from the wall. So there's going to be an X force or a horizontal force. It's also not going to let me lift and lower, so I'm going to apply a vertical force. Our rocker here is similar to a roller. It will allow for rotational movement. It will allow for movement in one direction. It will not allow for movement in the direction that's like perpendicular to it, which kind of makes sense, right? It's hitting the wall, it's hitting the floor. We wouldn't be able to go beyond that, right? So we have that. We do not have that sliding movement anymore. It's easier to kind of see that with rollers. We know, like, let's say we know the weight. We know the weight due to gravity is 9.8 kilonewtons. We know the weight of this is 23.5 kilonewtons. We do not know the reaction forces, but if we know it's in equilibrium, we can use variables for the reaction forces to find the final answer, to find the final reaction forces being the forces that are connecting us somewhere. So, two-dimensional things. Rollers or wheels are the easiest for me to see that this is the applied force. Front rockers or frictionless surface will be the same. You're going to have, where is it disallowing you movement? Where is it constraining movement? These we've been doing, it's just not something we've stated like this. So a short cable or a short link will impose a force in its direction. That is us finding our unit vectors, is figuring out the known line of action of that force. So this is something we have been doing already. We're just adding more elements, but usually the elements we add are easier here. Don't want to worry about this too much in this class. These would be the last two I'd worry about. So our pin is the one that we look like. Sometimes you'll see, we looked at in the last question, sometimes it'll be like a little, that type of thing. So we're fixed to the ground here, we're fixed to the ground here. It's constraining motion. It will not allow you to move up and down or left and right. However, this pin here does allow, so let me not add a constraint there, does allow for the rotation. Because it allows for rotation, I will not put a constraint in there. Rough surface, if it's a rough surface, that's going to constrain our lateral movements as well. So you'll see that that looks similar to the previous one. This one, frictionless surface, but that's where it's different. So pay attention to your problem statement, but you shouldn't see too much of those. The last one is a fixed support, and so that is like if you were to pour a beam in some concrete for structural purposes, it is going to apply a vertical and horizontal force, and it is also going to constrain your rotational moment or your rotational motion. And so it is going to apply a moment as well. There will be a moment applied when you disconnect from a fixed support or when you're trying to analyze a fixed support. Questions there? Okay. Let's not do these yet. Let's apply this problem a little bit more deeply. So here we have all of this information. This is the free body diagram we came up with. So our summation of forces in X, Y, and Z, if they were there, the summation of forces in Y in this case, in X and Y, need to be equal to 0 because it is an equilibrium. If it was not, this structure would be moving in some direction, which we know it's not. It's a fixed crane. So summation of forces in the X direction and the Y direction need to be equal to 0. What you could do is you could start, so there's different ways you could start. I said that already, so I'm going to say summation of forces in the Y direction equals 0. So positive AY needs to equal 9.6 plus 23.5, right? We need a positive Y to counterbalance all these negative Ys. That is what we're seeing down here. Get us 33.3 kilonewtons for AY, that reaction force at A. Regardless of if we had found that or not, if we analyze the moment about a point, the 2 points we would want to analyze the moment about in this case to solve for is either A or B. If we analyze the moment about point A, X has a moment impact of 0 and AY has a moment impact of 0 because perpendicular distance is 0. B would then have a moment impact, but that would be the only variable we had, which is what we have up here. So our moment evaluated at A. I'm going to start with my knowns. Our moment evaluated at A is equal to 0. This 9.8 is going to be applying a clockwise rotation at 2 meters away. So I'm going to say negative 9.8 times 2 minus, this will cause same type of rotation, minus 23.5 times 6 right? Perpendicular distance from A to this is 6 meters. So that's going to be these two terms, negative 9.8 times 2 minus 23.5 times 6. The last one we're going to have, the other moment that we have here is our B. I'm going to usually assume positive in my reaction forces, and then if my value is negative, I assumed wrong. Positive force at B would cause rotation that counters these. It's going to go in the counterclockwise direction. So that's going to be a positive value. We don't know the magnitude of this force, but we do know the distance it is applied. So knowing that the sum of these need to equal 0, we can solve for Bx, or the reaction force at B. Questions there? Okay. So then next we have our summation of forces in X. So if we had done our summation of moments about B, AY still would have had a 0 moment, B would have had a 0 moment, so AX would have been what you solve for up here. Either way, do the summation of forces in X direction to find the other one. You'll find it's the negative value of your first, and then we have kind of solved that system there. Questions on this? Okay. We lost most of you. It's okay though. 3-dimension is going to look similar. We'll go into that next week. We'll talk a little bit about the test and then I'll let you guys go. So test 2 is October 25th. It is focused on concepts from week 3 and 4, so from these homework assignments. First 2 weeks, anything we talked about there could be covered as well. There'll be some things like unit vectors don't go away at all, but they're not the focus. The focus is going to be on these homework assignments. For test 2, we want you to be able to find a unit vector for the direction of a wire or a force. Use that unit vector to calculate the force vector. So I, J, K equation. So basically, unit vector times force magnitude equals the force vector. This one's where the one that's like, I would least predict if I were a student here. Use the dot product method to find the angles between two vectors. That's the one that I think would be the hardest to predict to see coming. So I'm going to talk about that probably the most here. Use a cross product method to find a moment. Express the moment vector in I, J, and K form, which means you do not need to find the magnitude of it. You do need to be able to work with moments, but there are no force couples. There are no couples. And the equivalent force couple systems would not be there either. Equivalent forces. Good problems that you could practice. Take a look at the homework and the slides. We'll pull some of these questions potentially next week. So here are some good ones to practice. We'll take a look at them now. I pulled them up. Determine the moment about the origin O of a force. You're given the force vector, and you know that it acts at point A. The position vector of A is, so they're giving us R and they're giving us F. So basically we have to go in and do a cross product. I, J, K, R, F, line up their values. So like, let's say we were doing this one, it would be 1, 1, 1, and -2, -3. It may give it to you in a little bit of a different format. So it may say something like, oops, too far. It may say something like, given a force in vector format. So it may say something like F equals -2, -3 plus 5K. Find the force applied, if the force is applied at point. So like, instead of being written like this, it would say the force F equals, and that's in vector format, like it is here. If the force is applied point 1, 2, 3. Find the moment about the origin, right? The only difference between these two questions, so we'll say negative 2i minus 3j plus 5k. The only difference between this question and this question is that this one already has it in the vector format. So in this case, then your r would equal 1 minus 0 in the x direction, 2 minus 0 in the j direction, and 3 minus 0 in the k direction. And therefore, 1, 2, 3 would still be that vector. Does that make sense? Okay. While we're here, let's take a look at the other two. So the first one is going to be given the unit vector of a wire. Find the unit vector of a wire from image geometry. That'll be given point locations rather than angles, so not the cosines, the difference between 2 points. So something like this, or this, where you have to find the point locations and know the vector that connects them, the unit vector that connects them. You'll then be given a force magnitude, so you'll have to find the force vector. So you would multiply your unit vector by the force vector to get your unit vector by the force magnitude to get the force vector. The second question is that one that is find the angles between two vectors, and we're going to do that given the dot product. So this is a good example of that one. 3 cables are attached, determine the angle formed by AB and AC. So let's go back to that finding an angle between two vectors. And I'll have it. Product to find the angle between two vectors. Here we go. So this equation you will need to have for your test. This one right here. Let's even get rid of the end of it. Let's say it's this part. I can also change the color here. Sort of. So your vector P dotted with your vector Q. So when we're talking about our cross products, it matters which direction or which one you use first. With dot products, it does not. So P dot Q, the dot product between two things is you're multiplying their like values and adding the sum of that. So let's say P equals 1i, 2j, and negative 1k, and Q equals 2, 1, and 3. Okay, so P dot Q is going to be, we'll multiply the x values, 1 times 2. The dot product is also known as the scalar product. It is scalar in that scalar is the opposite of vector. It is just a value with no direction, meaning we're not going to have I, J's, and K's at the end of these. We're going to add PY times QY, 2 times 1 is 2, plus PZ times QZ, negative 1 times 3 is negative 3. So our dot product between P and Q is 2 plus 2 minus 3 is 1. That would be the dot products between them. To use the dot product in order to find the angle between two vectors, the dot product of the two vectors is equal to the magnitude of P times the magnitude of Q. So their magnitude is the square root of the sum of the squares. 1 squared plus 2 squared. So I lost my mouse there for a second. Magnitude of P times the magnitude of Q times cosine theta. If you were able to if we were able to so here, if we were able to, we know the locations, so we know their vectors, so we can calculate their dot product, and we can calculate their magnitudes. So the only thing we don't know here is the angle between them. So the only unknown variable in that would be theta. Solve for theta, and theta is the angle between the two cables. Questions here? Okay, cool. I am going to end it there. But next week we'll go over the homework, that third homework problem. We'll finish that one with the A's, so definitely work through that. And then we will do some rigid body stuff and some test review. So I would not miss next week if you can help it, and if you do, I would reach out to me to figure out what you're missing. Okay, cool. Thanks, guys.